In this lecture, we're going to look at a type of network architectures that we can train unsupervisedly without labeling our data. So these are the autoencoders. I'm going to start by explaining what autoencoders are. We already saw briefly in the first lecture, I gave an example of an autoencoder, but I'm going to talk a bit more about what they are and what the purpose is. And then we're going to look at different restrictions that we can impose on the encoding part so that we get something useful out of the autoencoder. This includes undercompleteness, different regularization methods, and so on. And then I'm going to talk a bit specifically about convolutional autoencoders. There are different types of autoencoders. We did not cover recurrent networks yet, so I'm not going to talk about recurrent autoencoders, but I'm going to give more emphasis to the convolutional autoencoders since this fits into this last part of the subject we've been covering. And I'm also going to talk a bit about other applications of autoencoders. Okay, so let's look at what an autoencoder is. Basically, it's a network that is being trained to output the same as we input into the network. So we have a loss function, typically a quadratic error, something like that, we use to measure the difference between the output of the network and the input into the network. And we minimize this function so that the network tries to reconstruct the input as faithfully as possible. What we are interested in is inside the network, in these hidden layers, specifically, typically at the center of the autoencoder, there is a layer which will create an encoding of the input, and that is the one we are interested in. So basically, we are training the whole network so that the output is the same as the input, because we want then to use some representation that is created inside the network, this latent representation in a specific hidden layer that we are interested in. So we can consider the autoencoder to be divided into two parts: the encoder, which transforms from the input space, any example, into this latent space, into this hidden representation inside the network. And then we have the decoder that transforms back into the same space as the input, and so reconstructs the input from this encoding. So the basic idea is that we have a composition of two functions, of the decoder and the encoder, and what we are learning is the function that composes these two. We want the decoder function applied to the encoder function. And the question is, why are we interested in this, since we already have x? So the basic answer here is that we have x, we are putting x into this function composition, but we can then break down these two functions, and we are particularly interested in the encoder. The decoder is just helping us train the encoder, and then we have this way of transforming our data into some more useful representation. And the interesting part, or most useful part here on the autoencoder, is that this can be done in an unsupervised training. This is a bit of a tricky concept here, because if we think of supervised versus unsupervised training from the perspective of the model itself, this is clearly supervised learning, because we have a loss function, we have this measure of the error, and we are backpropagating the error. So the autoencoder is being trained exactly like any other network by obtaining a feedback on the error that we are committing for each example, and then backpropagating that error to optimize the parameters. However, if we look at it from our perspective, in which the difference between unsupervised and supervised is basically the need for labeling data or not, then it's unsupervised, because whatever data we have, we can train an autoencoder. We don't need anything else. We don't need more labels to get our loss function. So from our perspective, this works as unsupervised learning, and we can use this to train the encoder part, which is the part that matters for us. So basically, the reason why we want to do this is that, as we saw before, these models, the deep neural networks, tend to identify useful representations along the network, and that's basically how they work. They transform the data into more useful representations, extracting the most useful features, and create those representations in hidden layers. And that is what we are interested in this case. What are the best representations that the network can find so that it can recover the input that we gave it? And that means it can transform the data without losing relevant information. And this can have advantage if you want to lower the dimensions of the data by, for example, narrowing the network into a hidden layer that has fewer neurons than the size of the input vector, or we can capture other types of structure in the data. So as long as we can force the autoencoder to do something useful and not just copy the input values into the output, we can use unsupervised learning to learn a useful transformation of the data into a better representation that extracts the more interesting features. So we are going to look at autoencoders as feed-forward networks, and this may be the most common architecture for autoencoders. But the reason we are only going to look at feed-forward networks for autoencoders is because we did not cover recurrent networks yet. In a few weeks, I'm going to talk about recurrent networks, and then we can see some examples of autoencoders for those kinds of architectures too. Since they are trying just to output the input, we don't need labels, and so from our perspective, they are unsupervised learners. However, we are going to need some kind of constraint, some bottleneck in the model or in the way it's trained to force it to get something useful in that transformation. Otherwise, we could just copy the input into the output, and that would not give us anything useful. So the idea of what a useful representation is and why we can expect this to work, I'm going to talk a bit more on the second lecture after the break. So we're going to take a more abstract look at representation learning. But basically, we've been using this idea that a neural network can create useful features, extract useful features along the layers, and that's what we're going to try to use to our advantage. So let's see some different types of autoencoders. Perhaps the easiest one to understand intuitively is the undercomplete autoencoder. An autoencoder is undercomplete if that hidden representation we are interested in, this H, this would be the vector of activations of the neurons inside the autoencoder in that layer that we are interested in extracting, if the dimension of this vector is smaller than the input vector. In that case, it's easy to see why the autoencoder has to do some useful work, because it needs to transform our data into a lower dimensional representation, but it must do it in a way that it can then recover the original data in the decoder part. So that representation in lower dimension must capture what is important in the data. And this forces the network to learn basically this compression or this dimensionality reduction of our data. We can do this by simply minimizing this loss function when we compare the x with the output of the decoder after the encoder. So this, remember, we are composing these two functions just to represent the two parts of the autoencoder. We have an encoder part and then a decoder part, but basically this is the whole network, and the loss function that we are using can be the quadratic error, for example, between the output and the input. And so this penalizes the error in reconstructing the input. If we just use a linear transformation in the autoencoder, this would be similar to principal component analysis, but without the constraint that the vectors must be perpendicular and so on. But basically, it's the same kind of transformation if everything was linear. But of course, with the deep neural network and nonlinear activations, we get something that is much more powerful than just a linear transformation. And so with a deep neural network to create an autoencoder, we get transformations that are much more sophisticated and much more capable of adjusting to the correct distribution of the data. There's one thing that we need to be careful about is if we increase too much the power of the model, then we may again stop learning anything useful. For example, suppose that the model is so complex that the decoder can simply take some index value, a single value, and from that it has memorized all the examples in the weights of the network, so it can reproduce any of the training examples just by knowing which example it is. In that case, the autoencoder is not storing any useful information. Everything is just being memorized in the decoder. So we need to take care, even though we are doing this in a way that from our side seems unsupervised, we should also take care with validation errors in training autoencoders, because that will give us an idea of whether the autoencoder is becoming too specialized on the training set, or it's capturing actually the real distribution of that kind of data. So this is a classical example of an undercomplete autoencoder, which I already talked about previously. We have an input that has a dimension of 8. These are 8 different values, but this is one hot encoded. So each of the 8 possible values in the training set only has a 1 and the rest zeros. And we are trying to recreate the same input in the output. So if it's 1, 0, 0, 0, it's the same thing that's going out there, and so on. But the hidden layer in the middle of the autoencoder only has 3 neurons. So it has to learn a representation of these vectors of 8 dimensions that has only 3 dimensions, but still can capture the structure in the data, and basically we get the binary encoding for different values. Another possibility is to not constrain the size of that hidden layer, which can even be larger than the input. In this case, we have an overcomplete autoencoder, but in any case, we are not putting a constraint on the representation here via the model itself. It's not in the architecture of the model. But we can constrain the representation by adjusting the way the model is trained. That is, to use regularization. So these are regularized autoencoders that we are going to train with some specific regularization, so that the hidden representation that we are interested in is useful for some purpose. So if we were just to do this without any regularization, the representation here at the center of the autoencoder would probably not be useful, because the network would just learn some trivial way of passing the input values to the output, because there is no reason to learn anything special in this case. But what we can do is to use regularization, so adjust the training of the network in a way that moves the autoencoder to learn something more useful in that hidden representation. For example, in a sparse autoencoder, we can force the hidden representation to have a small number of activations for each example. So we can estimate the probability of some neuron being activated by an example by just using the average over a batch of m examples. We can compute the mean value of the activation of that neuron I for each of these examples. So if we present 100 examples and the average there is, say, 2%, then we have this neuron firing on average 2% of the time. And now we can try to approximate this measured estimated probability of firing to some probability value that we want. For example, suppose that we want neurons to fire in the hidden layer. So in that particular layer here that we are interested in the center of the autoencoder, we want neurons to fire only 2% of the time whenever we present examples. So we can add to the loss function that measures the error between the input and the output, for example, the quadratic error. We can add with a small regularization parameter a measure of the difference between the way the neurons are firing and the probability with which we would like them to fire. For example, 2% or something like that. And we can do that by using the Kullback-Leibler divergence. We already saw this one. This is basically a measure between how divergent two probability distributions are. We can consider these to be Bernoulli variables because for each example, the neuron may fire or not, and then we are presenting sequences of examples or batches of examples, and we measure simply the divergence between what we are observing in these batches, that is the average firing of each neuron, and the probability with which we would like the neurons to fire. So this will, even though the network may have more neurons at this hidden layer than we are presenting, of course it can have less. Note that these are not mutually exclusive. We can use regularized under complete autoencoders too. The combinations, we are free to do them. But even if this hidden layer has a higher dimension, by forcing the neurons to fire only some of the time, so that for each example only a few neurons can fire, we are forcing that network to learn some particular representation in that layer. So specifically, we can force it to learn to specialize these neurons in identifying some kinds of features that only occur in a few examples. This is an example of a sparse autoencoder trained with NIST, and we can see here a set of 100 neurons in the hidden layer representation that were trained to be sparse. Oh, sorry, this was not NIST. This was on smaller images, 10 by 10. But in any case, this hidden representation here, the neurons are very specialized on specific patterns. Well, the images that are shown here are the images that maximize the firing of each particular neuron if we restrain the total brightness of the image to be constant. So we cannot just put an image that is all white just to make the neuron fire more, but if we keep the same balance of white and black pixels and gray and so forth, we can see different patterns that activate neurons. So this one is activated by this kind of white and black stripes in this direction, and then this one is a black corner and a white corner there, and so on. So they are all specializing in different patterns in the way that for each example only a few of them are firing. So we have specialized detectors for particular features that occur only in a few examples. Another way of thinking about this kind of regularized autoencoders is to, if we think about it in a Bayesian framework, is to imagine that we have some assumption about the prior probability distribution of the values. So we can think of this in the case of the sparse autoencoder as having a small number of activations as being equivalent to using the L1 regularization on the activation of the neuron. So instead of using it on the weights as we saw before, we are using it on the activation of the neuron. So basically we can also obtain similar results by penalizing the absolute value of the activation, and this is the same as using a Laplace prior. So sometimes you can see this discussed in this way in the literature. Basically, without going into detail here, if we assume a Gaussian prior, like we did with when minimizing the quadratic error, then we get this L2 regularization, where we penalize the sum of the square of those parameters. If we assume the Laplace distribution, then we have this Laplace prior with where we penalize the sum of the absolute values. But sometimes you can see this discussed in the literature as assuming some prior distribution, and that would be the reason for the regularization. But we can also look at it at a more pragmatical level, which is basically we want the neurons to be specialized for some particular features that only occur occasionally, and so we are penalizing the firing of neurons in that hidden representation, either by using, for example, L1 regularization. This could be an idea, or using the Kullback-Leibler divergence to some probability that we want it to have, or other regularization terms that we can use to force the network to only activate a few neurons at a time at that particular layer. So you can see in this paper there was an experiment with MNIST using different types of regularization for creating this sparse autoencoder. So if there is no penalty, we don't see anything interesting in these neurons in the hidden layer representation because they basically are not specialized for anything specifically and are just trying to find patterns that help minimize the reconstruction error. But if we use, for example, Kullback-Leibler divergence, you can see that these neurons are becoming specialized in identifying parts of handwritten digits, for example, these oblique slashes like this kind of curves, these curves, and so on. So different neurons are becoming specialized in different aspects of the shape of those digits, and so for each digit only a few neurons will fire, but that combination of neurons could already help us identify the digit. So it's capturing the way the data is distributed. But we can also use other penalties like L2, L1 norm, and so on. So there are different ways of trying to minimize the activation of the neurons in that encoding, and so force them to specialize in very particular features or patterns that occur only a few times in the data. Another possible way of training autoencoders is to add noise to the input. So what we are doing here is we, for example, switch off some pixels in the input or flip them, or put zeros in the input vector, something like that, at random. And so we have a degraded example. And we force the autoencoder to learn the original data. So it must learn to reconstruct the original data from a corrupt version by adding random noise. This is, in a sense, also a regularization method. We saw this. Noise injection is one way of trying to minimize overfitting and regularizing the training. And in this case, we are using that to force the autoencoder to learn something useful. Note that this can also be combined with other loss functions here, with undercompleteness by having a smaller representation here than the input, and so on. So do not see these classes as a partition where each autoencoder can only use one of these techniques. Often you can combine them in different ways depending on the problem you're trying to solve. But this would be another way of making the autoencoder do something interesting, and it's actually a very practical way because it's very easy to implement this. Every time you present examples to the autoencoder, you add random noise, and so you force the autoencoder to reconstruct the original one and remove the noise. So that's why they're called denoising autoencoders, because they learn to remove the noise from the image. Or the input in general. So the algorithm here would be very simple. We would just obtain a sample from our data, apply some kind of corruption with this noise, random noise, and then we train by minimizing the difference between the output of the autoencoder and the original input without the corruption. So our target is that the decoder can recover the original input from the hidden representation and not the actual input that we are giving to the network which has this corruption. Another possible penalization function that we can use is a fraction of the sum of the derivatives squared. So these derivatives are the derivatives of the activation of the hidden layer that we are interested in with respect to the values of the input. So it's not the derivatives with respect to the weights that we are using for training, but it's the derivatives with respect to the input. And what this is measuring is how sensitive our hidden representation is to small changes in the input. If these derivatives are large, then even a small change in the input can make the representation become very different. If we force these derivatives to shrink, to be small, we are forcing our network to learn a representation that is more robust, that is less sensitive to small variations, and so it will become more stiffer, more smoother in that part of the manifold where the data is distributed. And the reason why this is called contractive is that this will tend to make the representation more similar for examples that are close together. So it will try to bring them closer together when we are using this kind of regularization. This will also favor smaller weights, because if we have smaller weights on the network, we also will have smaller derivatives with respect to the input. And so it basically makes our representation conform more to the overall shape of the data distribution. This is related to denoising autoencoder because we can obtain a similar effect by adding noise. Adding noise to the data also forces the network to become more robust to small changes in the input, since for many different variants of the corrupted input, it will have to reconstruct the original one. And usually contractive autoencoders are harder to train because we need to compute these derivatives of all the activations in the hidden layer with respect to the input, and so this has an additional computational demand. So basically, if we want to solve some problem that we want to improve the way the hidden layer is capturing the manifold of the data, we can try to use noise first, and then if that doesn't work, maybe use a contractive autoencoder, because these tend to be more expensive to train. But the result is interesting in that this hidden representation will try to follow more smoothly the way the data is distributed. So when we look at the derivatives around each point, for example, we present the network with this O, the network, the contractive autoencoder trained with MNIST, we present it with this 0, and then we look at what are the main directions, the tangents to this hypersurface around 0. You can see more details on the paper if you want to see how they computed this, but this is not particularly interesting. The idea, what's important here is to have this idea that the hidden representation is creating a hypersurface in this space where the data is being represented. And when you look at the tangents in different directions of this hypersurface, you can see that they indicate meaningful changes to this 0 that could start going into slightly different zeros. So we reinforce a bit one of the sides, or shift a bit, something like that. But it's capturing some meaningful aspects of this example. The same thing when it's trained with these images, the CFAR dataset. You can see that it's the directions of the tangents to this surface here are showing variations in parts that are meaningful in the image. If we do the same thing with PCA, for example, if we project this into a lower dimension with principal component analysis, and then look at the tangents in that hypersurface that resulted, we can see that the combinations of pixels in those directions don't mean anything. So it's really nothing. PCA is not learning very well what the actual distribution of the data is, but which is expected because it's not a good way of learning these manifolds, and it's not giving us anything very useful in these directions. Okay, so let's look at one particular class of autoencoders that is related to the subjects that we've been covering recently when dealing with images. And these are the convolutional autoencoders. We can use convolutions to shrink the resolution of a multidimensional input. So basically, we are using convolution operations when we are interested in patterns in our input, but those patterns are not necessarily on those particular features. If we have time series or images or movies, things like that, we can try to find specific patterns that can be anywhere in the input vectors. So we use these convolution layers, we extract features from those, we are creating more and more filters, so these layers these tensors become deeper and deeper, but at the same time we generally use pooling to shrink the resolution, and so to abstract from specific locations in the input and just obtain those features. And we can do that to create a representation where we are identifying the different features and no longer care exactly where they appear, and we have a better representation of our unstructured input. We can do this in an autoencoder if we can go back and increase the resolution and reconstruct the original image. So this means that now we can train this whole thing unsupervised. We just try to measure the error between the reconstructed image and the original one, and this will allow us to train the transformation into some useful representation that we want. Now, we saw this briefly last week when we looked at segmentation, and we need this way of going back, and I talked a bit about how to do these convolutions again and upsampling to return to the original resolution. They are often called deconvolutional layers, but this is not a good name because it's actually not the deconvolution, it's just convolution. But there are several options that you can use. We saw transposed convolution, fractional stride convolution. Just to recall, the convolution operation that we saw, we have a kernel with some weights. We multiply the kernel by the inputs in a window. We add everything, the sum of those products, and this will fill in one place on the output vector. And then we keep sliding with a stride. For example, here we have a stride of 2, and we keep computing the values of the output vector. So if we use a stride greater than 1, or if we don't use padding, then the output will have a smaller number of elements than the input. And this is what happens with convolution. If we use a stride of 1 and padding, then the output can have the same number of elements as the input, but this way we cannot create an output with more elements than the input. So this is good for this part where we can use convolution and pooling, but then it doesn't work on this part when we need to increase the resolution of the image. So some ways of doing this. One is the transposed convolution, which slides along the output and does this kind of operation with each value of the input. So basically we are multiplying by the first value of the kernel and adding to that element of the output, and then we multiply by the second element of the kernel and add to that element of the output, and so on. And as we slide the kernel over the output and the input, we can generate an output that is larger, that has more elements than the input. So this is one way of doing a convolution so that we increase the resolution of the feature maps here. Another way is to pad the input with zeros, and this would be fractional stride convolution. we pad the input with zeros, and then as we stride along the input, since it's padded, it seems like we are moving at fractional steps, because when we look at it from the values that were in the original, the elements that were in the original input before padding with zeros, we are still going over them with our kernel and taking longer to scan through the whole input. There are, however, some problems with these approaches, and I'm going to show them later. So basically, the best way of doing this, the simplest and the way that doesn't result in some strange artifacts, is to use first upsampling with some kind of interpolation, for example, linear interpolation or simply nearest neighbors. This is what the upsampling 2D layer does in Keras by default, which is to create a higher resolution tensor from the original one by padding with values that are copied from the closest one in the original. So instead of padding at 0, we pad with the copies of the closest values. And then we apply a convolution, and the convolution will learn, this convolution layer will learn how to focus the higher resolution tensor a bit better. So if we do this just by using this nearest neighbor interpolation, just by copying values, we get a higher resolution image, but it's just a blurry image at a high resolution. But after we pass through a convolution, then it will be sharper, it will be more focused. So this would be the best way of doing it. There are other ways. For example, you can take a lower resolution map, apply several convolutions to obtain a set of lower resolution maps, and then shuffle them together into a higher resolution map. But this will be equivalent to these different approaches. So basically, I would say this would be the simplest one to use, and the one that avoids some types of artifacts that you can have with transposed and fractional stride convolutions because of the way the kernels overlap. So in this case, in transposed convolution, we have some kinds of overlaps here that are not quite the same as the ones here. So in different positions of the output, we are looking at different sums of different parts of the kernel. And the same thing here, when we consider that all these are padded at 0, we get some pixels or some elements of the output that will have larger, more intense values than others. And this creates these kinds of artifacts when we go back into the higher resolution images. Whereas if we do some interpolation with, for example, nearest neighbor and then convolution, we avoid these overlapping fields, and we avoid that kind of artifacts. So this would be my recommendation. Use, when you are going from low resolution to high resolution in the decoder part, use this two-step approach of first doing upsampling and then applying a simple convolution with a stride of 1 just to focus the image there. Okay, so one possible application of autoencoders of convolutional autoencoders that you can easily find on the internet is to create deepfakes. And this is an interesting application because of the way the autoencoders are used. The idea here is to transform someone's face into someone else's face. So we train an autoencoder that creates a representation of the face, a more compact, a better representation of faces. And then if we choose the right value for this vector, we can use the decoder to give us the face that we want. So if we change the encoding here, the code on this part, we get a different face. The problem is that this will only work for some codes, and we have no way at the start to knowing what is the code for the face that we want. So the problem here is how can we find the latent representation for the desired face? If we already have the face, it's easy. We pass it through the encoder, it gets us the correct representation, and then we feed it into the decoder and we get the face. But in that case, we need to have the face already, so this would not be useful. If we want to transform face between different people, what we can do is to train the same encoder for the different sets of inputs, for example, the different sets of faces, but we use different decoders for each of the sets. And basically this would be the idea. We are going to train this autoencoder using this encoder to create hidden representations of the faces of Jimmy Fallon. We can take several faces from the videos. We can even use data augmentation by distorting the faces a bit, so we make our data artificially larger and the autoencoder more robust, and we train it to recreate the correct face in the correct position after this deformation. So note that we are also including here a bit of denoising into this autoencoder. It's under complete 2, the representation is much smaller than the original vector and so on. And now we do the same thing with John Oliver, but while we are using the same encoder, we are using a different decoder, and we are going to train this alternating between these decoders. We are going to train a mini batch with Jimmy Fallon and then another one with John Oliver and so on. The encoder is always the same, but the decoders are different. And basically what we are doing here is we are training the encoder to map between these faces, regardless of whether it's Jimmy Fallon or John Oliver, but to map these faces into this hidden representation that is common to both types of faces. But we are specializing each decoder to map from the hidden representation to one of the particular types of faces. So we have one decoder for John Oliver, one decoder for Jimmy Fallon. And now after we train this, what we can do is to switch the decoders. So if we feed an image of Jimmy Fallon into the encoder, but then use the John Oliver decoder to reconstruct from that encoding, we get the John Oliver's face, but in the same position, orientation, and expression as we had Jimmy Fallon. So this is how we can then automate the replacement of one face with the other in lots of frames, in videos, and so forth. Another useful application or interesting application of convolutional autoencoders is for unsupervised segmentation. We saw this UNet last week for supervised segmentation, where we have the input image here. We have a target mask for the different classes of the input. So remember that segmentation involves assigning each pixel to a different class. This is something that you're doing in the assignment, for example. So we have the target mask. This is supervised. And what we're doing is passing through this architecture that already looks like an autoencoder, apart from these skip connections here. And we convert the original image into lower resolution feature maps, but with an increasing number of filters. We have here a representation of the image that abstracts from the different locations, and then we reconstruct here an image of the same size, but now our target is to approach as much as possible the segmentation masks that are provided. So this is supervised learning, because we are trying to approach these labels that we are given for each pixel. But suppose that we do this. We concatenate two UNets. This is called the WNet. And we are starting from the original image. We use one UNet here to create a representation that classifies each pixel into different categories. So we can have here K layers to specify K categories, for example. And then we use again a UNet to go from this representation back into the original image. And this would be the reconstruction loss that we're trying to minimize by minimizing the difference between the output of the WNet, which will be also as close as possible to the original image and the original image. But we want this autoencoder to learn something useful. So here we have this soft cut loss function that tries to force the representation here to split apart the image in the best way possible. So let's look a bit at this loss function. If we have a graph, we can split the graph between two subgraphs. So let's say we have a graph and we split it into a set of nodes A and the set of nodes B. We can compute the cut for this partition of the graph by adding all the weights between nodes in subgraph A and nodes in subgraph B. If we minimize this cut, we can find which part of the graph we can separate from the rest, affecting the smallest total weight possible. Of course, this will tend to split the graph into a very small part. So we have a large part and a very small part, because that way we will have a smaller number of edges connecting these nodes. For image segmentation, this is not very good, and so these authors proposed the normalized cut, which is when we partition a graph in two parts, A and B, we can sum the cut of this A and B. So basically the sum of the weights of the edges that we had to remove to separate these two sets, divided by the association of A, which is basically the sum of the weights of A to everything in the graph, to the whole graph. And the same thing for B. So this normalizes by dividing the cut, that is the sum of the weights of the edges that we have to remove, by the sum of the weights of the edges of the each of the subgraphs to everything else in the graph. And this will tend to find those weaker frontiers in the graph where we can cut without losing without cutting edges that have great weight. So the idea here is that we are training, alternating, presenting one mini batch, finding the minimization of this normalized cut here, and adjusting the parameters of this part of the network to minimize the soft cut. That is to force the representation here to split the pixels into classes that are more natural to the image. And then we do the update for the whole network to minimize the reconstruction loss. And we're going to alternate this here. Of course, there are some complications here. So when we have this representation of the pixels in different classes, if we have k classes, we're going to use k filters, and we're going to assign each pixel to the filter that has the maximum at the activation. Unfortunately, the maximum we cannot differentiate the maximum, we cannot compute the derivative, so the authors use a more sophisticated formula using this soft normalized cut, but the idea is similar to what we are doing in softmax. Note that when we have multi-class classification, we could in theory assign the class to the highest value in the output, but this is not, we cannot compute the derivative of that maximum function. So what we are doing is we are computing the probabilities using the softmax function and then approaching those to the one hot encoder target or something like that. So this is the idea here, because we cannot compute the derivative of the maximum. And then there is also the question of these edges. So in abstract, we can understand how to do this in a graph, but if we want to do this in an image, we need to specify these graphs. And the idea is that, for example, here in an image, we can consider each pixel and pixels in the neighborhood and define the weights of the connection between the pixels as a function of how similar they are or how close they are together. We can even disregard pixels that are far away, only consider small neighborhoods, and compare, for example, the color distributions or the local pattern for the texture or something like that. And that way we can create these graphs for each image automatically, even before training starts. And these are the edges that we are going to use for each image when computing these normalized cuts and trying to find out where to cut the image in a way that minimizes cutting edges between pixels that are very similar one to the other. This WNet also includes some post-processing for smoothing the regions that have been segmented, for clustering the pixels and so on. But you can see here the results at different levels of post-processing. That happens when you have an image, for example, this bear hugging this tree, and then you have these levels of smoothing and segmentation where you can find the different parts of the image that were segmented into different classes. Now, the interesting thing here is that this is done without supervision. So we do not have these target regions and then train the network to try to approximate them. We are just training the network with the image and doing this method of training by minimizing the reconstruction of the same image, but also minimizing the values of those cuts, that is, minimizing the weights between the pixels which we are separating into different categories. And so if we create those weights in the way that captures the different textures and colors and brightness in the image, then we can have the network learn how to segment these images without supervision. Okay, so other applications of autoencoders. One very obvious one is manifold learning, as we are doing, for example, with under-complete autoencoders, reducing dimensionality, or using contractive autoencoders to approximate the distribution of the data. We are trying to find the manifold where the data is distributed. Basically, a manifold is a set of points that is close to an Euclidean space in the neighborhood of each point, but has a lower dimension than the space in which the points are distributed. One example would be points distributed at the surface of a sphere, which we can convert into a two-dimensional map, as we do with points in the surface of Earth. So we saw this in machine learning last semester. The idea here is that if we have our data in a higher dimensional space, but it actually conforms to some lower dimensional structure, we can find some representation that better captures that lower dimensional structure and reduce the dimension of the data by capturing this manifold adequately. So this is something that we cannot do very well with linear transformations like PCA, but we can do it with autoencoders. So consider, for example, this data set, the banknote data set, which you're going to use in the exercise today. We have a four-dimensional data set. If we try to reduce that to 2 dimensions with PCA, we still get a very large overlap between the classes, and the representation doesn't seem to be very good. But for example, using this autoencoder, so this autoencoder has 64246 neurons in the hidden layers. There is, of course, 4 inputs into this first layer, and then we need an additional layer with 4 neurons at the output so that we can have the same output as the input. But since this is a regression problem, all of these values are continuous, these output neurons don't have any activation, and we just train the whole thing to minimize reconstruction error. And then we just look at the representation here for each of the examples, and we can plot it on a 2-dimensional chart. So you can see that the autoencoder managed to find a much better representation of the data than PCA, and this can be done without knowing the labels. I'm actually using the labels to plot this representation with different colors, but training the autoencoder does not include the labels. It just captures the way the data is distributed, and in that representation, the real and fake banknotes are very different from one from the other. So this works basically because we are forcing the autoencoder to do two different things. One is to reconstruct the input, but the other is to respect some constraint that we are imposing. For example, under completeness, where we reduce the dimensionality of the representation when compared to the original data, or some regularization that we impose, and so on. Remember that if the autoencoder is too powerful, it will not learn anything useful. Everything will be stored in the decoder, and the representation itself will be irrelevant because the autoencoder just needs to know which example that one is, and then it will reconstruct it. So look at the generalization error of the autoencoder by using a validation set, and try to optimize that in order to get a better representation in this lower dimension in the manifold of your data. So, and this brings us to another useful application of autoencoders, which is detecting outliers. If we train the autoencoder on some data set, the autoencoder will learn what the distribution of that data is, and so it can recover examples which belong to that distribution. If then you try to present a completely different example to that autoencoder, the reconstruction error will be higher because it's outside the distribution that the autoencoder learned. So this is a good way of identifying outliers. Suppose that you have a data set where most of the events or the examples are normal. For instance, you can have the activity log on some server, and most of the connections to the server are perfectly normal things. And you can take all of those examples that you know don't have anything strange and train the autoencoder with that. And then if something strange occurs, even if you don't know at the beginning what it could be, and you never trained the network to identify those strange examples, since the network was trained only with normal examples, then it's likely that the reconstruction error for this anomaly will be higher. And so you can use the reconstruction error to detect these outliers, these anomalies, even if the network was only trained with the regular examples. So this is one application for autoencoders to detect anomalies or outliers in our data. Okay, so to sum up, autoencoders, the basic idea is to reconstruct the input in the output, but when we impose some constraint on what's happening inside the autoencoder, we can get some useful representations in that central hidden layer. I looked a bit more about at convolutional autoencoders and some specific applications, and then more general applications, but one very used application is dimensionality reduction, or compressing our examples into a smaller representation, more useful representation. We're going to talk a bit more in the second lecture about this, so I'm going to start at 10 minutes after 10, after a short break. And if you want, you can read more in depth about autoencoders in chapter 14 of the book. So see you soon.